Right, so we will reconvene now with the next presentation, which I understand will be a joint presentation by Priya Jawal and Marta Padilla from CARIS based in Fredericton, New Brunswick. And the title of the presentation is GeoAI, Exploring New Opportunities Through Deep Learning. And is it you, Marta, who's starting, or?
Yeah, it's me.
Okay.
Yep. So hello, everyone, and welcome to our presentation. Today we're going to talk about geospatial AI, and we will exploring what new opportunities deep learning has brought into the geospatial and hydrospatial community. We are Teledyne CARIS, and here today we have Priya Jawali. She's a co-op developer at CARIS and has been working with us for the last 8 months, making valuable contributions to some of our AI development and more recently our web team. We also have Burns Foster, who is our innovations manager. He's been with CARIS for about 12 years, and on the last few years he's been leading our R&D projects, and the main one being our AI platform. And then myself, my name is Marta, and I'm a cloud developer at CARIS, where I work with cloud technologies and web development for geospatial. And now I'll pass it on to Priya, who's going to give a quick background introduction about AI and deep learning techniques applied to geospatial data.
Thank you, Marta, for the introduction. So we begin with artificial intelligence. Today is a buzzword that is staging the future of innovative transformation in the field of technology. The term, moreover, refers to any human-like intelligence exhibited by a computer. It can be a robot or any other machine. Machine learning is a subset of artificial intelligence that uses algorithms to build systems which have the ability to learn and improve from the experiences. Deep learning is a subset of machine learning that teaches itself to perform a specific task. So it's a technique that is inspired by the way how a human brain filters information, and it is basically learning from the examples. So as we all are aware about the traditional programming, in contrast, the machine learning has enabled the computers feed on the real life data, and the machine learning algorithm depends on the features to extract patterns from it and make better decisions by itself. So sometimes you might need experts to identify or feed in the features that might affect the outcome. So what if machine learning figured out what features should be just by looking at the data? So that's where deep learning comes into picture. So here we have the satellite image, and we are looking at the computer program might look at each pixel by image and try to determine whether it's industrial, green area, or a residential type of image. So we are basically filtering it out on the basis of the features and the layers of the model. So for example, if it is sparse or continuous, if the structure is that of a building, and so on. And we classify it into various categories and give them labels. So one such blend of artificial intelligence is encountered with the geospatial sciences, and it merges with the solution-based approach and sharp analysis of artificial intelligence, becoming the geospatial or the GeoAI. And one area of artificial intelligence where deep learning has done exceptionally well is the computer vision. And we will look at the different vision tasks to see how what we are doing at CARIS. So the simplest is image classification. So looking at image of some sort, like the image from the satellite, we can look at them and say that's bridge, that's a forest. So it's just a simple task of assigning labels to images and try to identify what it is. Further, we have object detection, which is a little more advanced. And we have satellites going all the time, but we have a vast data. And the task is like to find one relatively small object in all this data. It's where object detection through AI becomes quite important here. For example, if you are searching for ships in the oceans or whales or the icebergs. Another important task in is the semantic segmentation, in which each pixel of an image is classified as belonging to a particular class. For instance, for the 2D satellite images, you can easily identify that's a road, a farmland, or water. And for the 3D point cloud, you can identify every object within the same, like talking about the indoor point cloud. Finally, it's the instance segmentation. You can think of this as more precise object detection, in which the precise boundary of each object instance is marked out. So you may want to find specific objects within point cloud as well as from the lidar. So here, for example, it's shown as the cars have distinctively have the precise boundary which distinguish it from the different cars. To sum up, we have this vision task. So this is the first image classification, where we just assign labels to it. And then we have object detection, where we have a bounding box to it. And based on the categories, we segment it. This was just some background that we could be applying in geospatial data. Now Marta will talk what we have actually done so far at CARIS.
Yeah, thank you, Priyal, for this great introduction. And now I'll be talking about what we've been doing in the last few years at CARIS in terms of GeoAI. So we set up our vision a few years back. There is a huge amount of data coming from manned and unmanned platforms full of oceanographic and other sensors. And this data can be streamed through global high-speed internet connections into a cloud platform, where the data could then be distributed in real time using international standards to the end user. So this is how we came out with this concept of geospatial, hydrospatial in the cloud. So this vision has been driving the latest innovation in our product lines, and cloud technologies and artificial intelligence are essential in meeting these needs. The cloud offers the reach, scalability, storage capacity, and processing powers for this vast amount of data. And artificial intelligence allow key decisions to be made more quickly and efficiently at scale to avoid being overwhelmed by this data volume. Decisions that before implied a big amount of manual intervention. So our main businesses involve point clouds from multi-beam sonars, and more recently also LiDAR platforms. We develop software to process these points clouds and eventually create valuable products from them. So this generates the research question of how to deal with point clouds in AI. This is an exciting but relatively new area. And the main challenges are related to the fact that the point density can vary quite a bit and the point cloud is irregular. So therefore it's difficult for computers to modulate efficiently. So then to take over this challenge, we came up with an efficient architecture for AI. At a very high level, what we do is we take the point cloud, then we divide it into smaller chunks called voxels. This voxelization is usually based on point density using our variable resolution technology. Basically, what it does is try to find square areas in the point cloud of constant density and then create voxel grids out of these tiles. This allowed for a significant data reduction, but keeping the valuable information and the shape of the data. These voxel data structures are efficient to feed into a GPU, which does all the magic inference and gives back a label that we then can apply back to each point cloud of each point of the 3D point cloud. And an important part of this architecture is that we can easily take that GPU middle piece and stick it into the cloud. So it's available to everybody, and the cloud takes care of the complexity and computing power. So this is the architecture we use to develop our cloud-based AI platform to host our current and future AI solutions, and we call it Keras Mira AI. This platform is backed by Amazon Web Services, offering a robust platform with broad scalability and availability, and obviously the reliability of AWS, the lead company in cloud services and technologies. And I would just like to mention that we also have an on-site version available, so for users that they still want to have that option, we do offer that possibility, so no connection is required, and you will have to deal with specialized hardware and upgrades and updates. So digging a little bit deeper into the cloud architecture itself, a Keras user is able to connect to the platform from our our processing software, HIPs and ZIPs, or onboard. So the workflow is seamlessly integrated. We leverage Route 53, Amazon DNS service, to capture the request and route the traffic to different servers based on the latency. We have clients on different parts of the world, and we have deployed the same architecture on different regions to offer the best availability. Then this request goes through a load balancer into an EKS cluster. EKS is the Amazon service to manage Kubernetes clusters, and inside the cluster we have different node groups, one with GPUs and other for general purpose computing. So these two node groups scale differently depending on demand. So this way we achieve broad scalability. And finally, for user authentication and authorization, we leverage Amazon Cognito user pools. And in this cloud architecture, data security is obviously very important. All the connection uses HTTPS, and obviously a strong password is required to sign up into our service. But the most important part is that all the data sent to the cloud is encrypted and anonymized, and we don't store data anywhere. When we create the voxel grid, we give it a false origin, so if the data is captured along the way, there is no useful info to reconstruct the origin of the data. And obviously, AWS also provides the best-in-class security monitoring. So we've leveraged services like CloudWatch and identity and access management to achieve strong security and monitoring. So now I'll pass it back to Priyal, who's going to focus on our first GeoAI service offering that is implemented in our cloud AI platform, the Sonar Noise Classifier.
Thank you, Marta. Terrestrial Keras' Sonar Noise Classifier is the first tool in the cleaning data, and the cloud tool is directly available to Keras SIPs and onboard users from directly our applications. And it also automatically identifies the vast majority of sonar noise and removes it, significantly reducing the need for manual cleaning. It also leverages the Keras variable resolution technology, and it is designed to process large data sets in no time and very efficiently. we come to the workflow of Sonar Noise Classifier. So it starts with the HIPS and SIPS filter workflow, and we first import and georeferencing the data, then run the noise classifier. So the AI here assigns a noise confidence from level of 0 to 100 to every point. 100 means it's definitely very noisy, and then the next stage is to review noise confidence, and the last stage is to set threshold and filter the data set. So as you can see in this example here, everything above 68% noise confidence will be filtered. Talking about the benefits, the Sonar Noise Classifier was designed to fit into the processing workflow, and it also leverages the Keras variable resolution technology as we discussed. And in terms of saving time, based on the trial, users can expect significant time savings in their processing workflows. So to make it simple, the worse the data is, the more time you save. To talk about the performance, I would like to mention that we have a sister company, Teledyne Optic. We work very closely with them, and they make airborne LiDAR sensors. We are working both airborne LiDAR side and the hydrowater side and trying to handle the noise problem. Teledyne Optic also makes LiDAR bathymetry. So in the results here, basically Sonar and LiDAR, in terms of getting rid of the noise, we hit up to 90 to 95% of accuracy. And in the data preservation, we also reach on the higher side of 98 to 99% for Sonar and LiDAR. The Bathymetric LiDAR is 70% because it's still in development and haven't finished the training yet. Once the training is done, it's expected to be on the levels of Sonar and LiDAR. And on the other hand, in terms of time saving, the time is saved if the data is really noisy. So ironically, the time saving increases the worse your data is. And here are some samples of the noise reduction sonar. So this is the noise reduction sonar has done a really good job. It has kept the data intact, and as you can see, there is the noise on the above portion, and it has done a good job at removing the noise. And this is the LiDAR, and this is the airborne part, which is quite challenging. So when you get into a scene like this, where you have whole mountains cutting through the noise bands from the atmosphere, it becomes quite difficult to get rid of the data. So nice thing of AI is we can train on the scene, and then even if it doesn't do a perfect job, it actually saves quite a bit of manual cleaning time to get rid of that and to get the end results. And on the LiDAR bathymetric side, as you can see, the sea floor getting rid of the bad reflectors in water column and the water surface itself.
So this is all we had for you today, and we hope you're the same excited as we are about these new GeoAI opportunities, and we're sure we will expand in the capabilities of our platform in the very near future. Thank you.